So how's it going with your homework? Is it going well? Is there anyone who have done already or finished it, the homework? Okay, maybe a few students. So even though the homework is to write some programming kind of code, but you will find it mostly deriving those gradient equations, especially in the vectorized form. Okay, so let me continue a little bit about this vectorized form and its gradient. So we learned at the end of the last lecture, we learned that this vectorized form of a computational graph is nothing but just a compact form of just a computational graph, which is composed of all the scalar components, right? And then it's just a rearrangement of our scalar variables or parameters into a vector or matrix form, right? And then now, I think you guys are already studied the derivation of dx being equal to dy times W transpose, right? So it was in the video that I asked you to watch, right? Okay, and and one thing that I want to note here is that this guy is really, it's not really dx. Its meaning is df over dx, right? So it's not like dy over dx and this particular denominator or numerator. It's really, the numerator is fixed as our final loss function f, right? And then it means the partial derivative of that common function of our loss function with respect to a different variable. Here, the variable is x, and this guy is df over dy. Okay, so okay, so I think you guys understand this equation, and then now so in this equation we in this linear layer we have w and x, and we have y here, right? So this is just a simple vectorized form of a fully connected layer where y is w times x, right? And then now we have to obtain the partial derivative with respect to each of our input variable. So we understood this part of dx being equal to w transpose dy, but let's derive this part of dw over df. Okay. So in this case, just like the video that in the previous video, let's just think of a different representation of this computational graph into this form. We have 3 input node and 2 output node, and this is y1 and y2 and x1, x2 and x3, and then we have w, which is representing this fully connected layer. Okay, and then okay, and then so this vector output is represented as w times x, right? And then let's enumerate each elements in our W as W11, W12, W13, W21, W22, W23. Okay. Okay, and then we want to obtain this guy, right? df over dw, and then that part is still the same, I mean having the same shape of 2 by 3 matrix, right? And then each element in this part will be dw11, dw12, dw13, and so on, right? Let me just finish it. Okay, and then now let's just fill that out, each element by element. So what is this gradient with respect to W11? So in this case, where is W11? So if you imagine we have W11 here, right? And then it is actually multiplied and then added together to form Y1, right? Okay, so this Y1, I mean, yeah, this W11 and X1 and multiplied, and W12 and X2, and these are multiplied, 13 and X3. Sorry for bad handwriting, but you get the idea. And we get the addition at the end, right? And then if we reach the gradient arrived at this point, and the gradient is dy1, right? Because this guy is our output node of our interest. And then we have an add gate here, so gradient will be multiplied, I mean duplicated, right? And so the gradient will be all the same, right? And then what about this multiplication for the gradient kind of conversion? It is a gradient switcher, right? So we want to have the gradient with respect to W11. So we have to multiply this guy with X1, right? Okay, so this guy is dy1 times X1, right? And then what about the gradient with respect to W12? It is similarly obtained as this guy, right? So far so good, right? So does it make sense, right? 표정들이 안 좋은데. 이해 가죠? 네? 안 가는 사람? 뭐 되게 쉬운 건데 그리고 또 되게 중요한 거라서. 네. Okay. Okay. So we got this, right? So this is our gradient with respect to this whole matrix W, right? Or in short, this guy, right? Okay, so I need to separate it. Okay, and then let me just rewrite it as a outer product form. And how? So as you can see, each column will all have the elements as dy1 and dy2, right? And all rows will have x1, x2, and x3. And so it can be factorized into this form, dy1 and dy2 as a column vector, and x1, x2, x3, right? So yeah, this was coming, yeah, I mean, this was part of 4 different perspectives of matrix multiplication, right? So, yeah, suppose we perform this matrix multiplication where we have 2 columns and 2 rows on the left and right respectively, and then we know this times this, right, and this times this. Those 2 outer products are added together, right? And so this guy is x1 and y x2, and this row is y1 transpose, and this is a y2 transpose, and x1 and y1 transpose plus x2 and y2 transpose, right? So this was fourth perspective of, yeah, understanding matrix multiplication. I mean, if you don't have much idea about this, and then please review what I asked you to watch in terms of matrix multiplication. Okay, so in this case, this is nothing but a special case where we have just a 1 column and 1 row, and being able to represent this whole matrix as a single sum of outer product, right? And so if you just do this computations mechanically, and then you should be able to, you should be able to see this one being true, right? Okay. So this guy is dy times x transpose, right? So this is our conclusion. I mean, yeah, the derivation of our derivative of this matrix W in the fully connected layer in this vectorized form. Okay. Okay, and then let me So this is not the end. I mean, in order to properly solve our homework, we need a 1 step further from this, which is kind of a batch version. I mean, the vectorized version of using our batch instead of just a single column of an x and y. So, when involving our batch, and then we consider within our mini batch, we have a multiple x values and also y, multiple x vectors and y vectors as well, right? Okay, so suppose we obtain, so given the first input vector 1, 2, 3, and then suppose we obtain the output as 4, 5, and then as a second data item, which is maybe 6, 7, 8 as another input vector, and then we obtained maybe 9 and 10 as another output vector. Okay, and then our vectorized form will have this form: 1, 2, 3, and 4, 5 as an output vector, right? And then in terms of the next input vector, we concatenate it column-wise over here. And then 6, 7, 8. And then what is the corresponding output? The output will be placed over here, 9 and 10, right? So this one is actually, this one can be viewed as the another perspectives of matrix multiplication. So if you guys remember another type of a matrix multiplication, and then it can be viewed as a column combination. So we have a 3 column on the left right? And then what are these? So what's the role of them? So these will be working as a linear combination coefficient for each of these three columns, right? And then we linearly combine them together, right? So yeah, maybe, yeah, let me just give an example of maybe 1, 1, -1 and 0, and 0 and 1. And then this 4, 5, I mean, it's a hypothetical example, but this 1, 1 and -1 and 0 and 0 and 1 and 1 times and 2 times and 3 times, and then we add them together, right? So this column combination will form the first column of an output matrix, right? And then what about the second column on the right? So that will work as a linear, the new linear combination coefficient that will replace this guy, right? So 6 and 7 and 8, but we use the same columns, right? I mean, common set of columns provided over here on the left, right? But using different linear combination coefficient, and that will form the second column of our output, right? Okay, so this was a column combination view of a matrix multiplication. Okay, and then let's go back to this derivative with respect to our matrix W. Okay, and then let me just write this guy as x1 and x2, because they are two different data items that we have, right? So those two will form our batch, right? And then this guy is y1, the first output, and the second output, right? Okay, and then so we have W here. Okay, so this whole equation, I mean this single equation, yeah, is equivalent to like W and x1 and the y1 and W and x2 and y2, right? So this is just the same thing that I just explained, because using the same matrix W, using the first column, we will form the first column, and using the second column, we form the second column. So they can be entirely separated from each other. Okay, so that way we can easily write them in this form, right? Okay, and then if you imagine the backpropagation and like generating the loss, and then causing some gradient, and then doing the backpropagation, and then loss will be incurred from each of our data point, right? So this is the first data item, and then this is the second data item, and each of them will have their own loss value and then their own gradient values, right? And so at this point of on y, we will have its own gradient, which is our d of y1 and d of y2. And these are actually a vector, right? These are actually a vector. And also this is another vector, which is two-dimensional vector. I mean, again, we are dealing with this fully connected layer like this, right? And when putting the first data item, and then we will do the forward pass, and then do the back propagation, and then we will have the gradient for this, for the first data item, right? And then, okay, so what about the gradient with respect to W? So W will have also its own gradient coming from the first data item. And what was the equation? That equation is this, right? So this was the gradient, the derivation of the gradient with respect to W, right? When considering only a single data item, right? Okay, so we have the gradient caused by the first data item and the second data item, right? And then how should we combine those two gradients? So those two different gradients caused by the first and the second data items, and they are causing the gradient with to the same guy, same W matrix, right? So if you imagine, okay, so this is a little kind of messy but clearer clearer form of our computational graph, right? And then this was our first feature, but it's coming from, it's from the first data item, right? And then what about the second data item? So the first feature of the first data item and the first feature of the second data item can be viewed as different data items and thus different nodes in our computational graph, right? So it seems that you guys don't understand properly, so I get to explain more and more details. But suppose we have two data items. Let's go back to really simple a linear regression where we have our model is just y equals ax, and the first data item is a 1, and the target value is 2 and maybe 5. Okay, so in this case, what is our loss function? A times 1 minus 2 squared, a times 2 minus 5 squared, right? So this is our least square loss, right? And how do we represent it as a computational graph? A, right? And this is the first data item's feature, and this is the second data item's feature, right? And thus x1 and x2, right? And then multiply together and maybe y1, and take the difference between them and then take the square of them. Okay, and also this A is also connected with the second data item, right? But A is the common node, but x1 and x2 are two different nodes because they are two different data items, right? And thus y2 okay, and then they are finally added together. So this is our final loss function that represents this function, right? Okay, so my point here was this parameter A is connected commonly to the first data item and the second data item, right? And thus this A has actually branch, right? Branching into two different paths, right? And when a single node is branching out, and then how do we deal with their gradient coming from this flow and this flow? They are added together, right? So that was multivariable chain rule, right? So all these previously learned stuffs are connected together, right? So there is no magic at all. So that's the reason why you really need a solid background from the beginning. Okay, the fundamental should be strong. Okay, so back to this part. this W, which is our vector node, is commonly connected with the first data item and the second data item, and then each of them will cause or generate this gradient, and they will be what? Added together, right? Because our loss function will involve the summation, I mean the summing of all the losses from each data item, right? So far so good? Okay, so we can then rewrite this dW as simply the sum of these two. Okay, and then we were able to factorize this out into dy1 and x1 transpose, right? And dy2 and x2 transpose, right? So far so good, right? And then how can we rearrange them? We can further rearrange or rewrite it into this form. So this is really this sum of outer product, right? So here each of them is just a product of column and row, right? Two vectors as an outer product, and they are added together, and then we can rewrite it into a single matrix multiplication form. And how? Yep. So this guy comes here, and this guy comes here, okay? And then this guy is over here, and this guy is over here. So this is just a rearrangement with respect to columns and the rows, right? Okay, so our final conclusion is dy and dx transpose, where this y has the columns of the gradient coming from each data items like this, and then the matrix x, so we shouldn't have d over here. So x is just a matrix whose rows are each data item's input vector, right? So this is our final vectorized form when considering the mini batch or the data items as also the vector to vectorize. Any questions about it? 다 이해 간 거예요? Okay, so if you don't understand, I can explain it with no problem. I mean, explain it again. So feel free to just ask anytime. Okay. So it's almost always true that you are not alone when you don't understand something. Okay. Okay, and then so that's probably it for the backpropagation. And one big thing that you have to understand while doing the homework is the backpropagation derivation of the backpropagation for the softmax layer. So the softmax layer. Okay. So yeah. Yeah, maybe when we have 4 input nodes and then the 3 nodes corresponding to each of our class. Maybe it's dog and cat and maybe sheep. And you guys know how the softmax works, right? And then suppose, yes, so this value is 2 and 7 and -1, and then you know how to convert them or transform them into a softmax layer output, right? And then which is some probability value, and that suppose that probability value was maybe 10%. And 85% and 0.5%. Okay. Okay, and when when our loss is softmax loss or cross entropy loss, and that image, I mean, the input has a ground truth as maybe cat. Okay. So in this case, what is the gradient at this vector? Okay, what is the gradient at this vector? So this output, I mean, first of all, what is the loss value? Loss is negative log what? Point? What is the loss? It is our loss, right? Because currently the ground truth node has the output of 85% from our forward propagation, right? Okay, and then just if you derive the gradient with respect to each of our softmax probability values, and then what is the gradient? I mean, this, suppose this, let's call it as a vector y, okay? And then what is dy? What is dy? So just like the fully connected layer that we saw, okay? So just like we have some activation over here, right? And then during the backpropagation, we will have some gradient value arriving at those nodes, right, from the backpropagation, right? And what is that gradient arriving at this vector y? Okay, so if if you guys did a homework and then finishes the derivation of it, and then it is simply the difference between this guy and this guy. So we basically subtract this 1-up vector, I mean this output vector, from the ground truth vector. Okay, so 0. No, sorry. This vector minus ground truth vector, 1-up vector, right? And so this is a 0.1 and negative 15 and 0.05, because we have a corresponding ground truth value as 0, and so 0.1 minus 0 will be 0.1, right? And 0.85 minus 1 will be negative 0.15, right? And then how can we understand this gradient value? Okay, how can we understand this gradient value? So this is our dy, and then so first of all, can we directly do the gradient descent update on this y? Is it possible? So let me ask again. So in this case, can we directly update this y using the gradient descent update? So my expected answer is no. So because this y is not our parameter, so they are just a neural net, intermediate output in our neural net, right? Our parameter that we can directly update is involved over here, right? And also but on the other hand, in this softmax layer, I'm not gonna write the softmax equation, but in the case of softmax function, there is no trainable parameters. It's just a fixed function, right? And so from this value to this value, so there is no parameters involved, and also these are not our parameter that we can directly update, right? Okay, but let's just imagine we can update these values directly, okay? And what does that mean? So if we could do the gradient descent update, and then this value, 0.1, should be updated in the following manner. So suppose our step size is a point, maybe 2 times 0.1, right? Because this is a current value, and this is step size, and this is our gradient, right? So what does it say? So currently, the probability assigned to the dog class is 10%, right? But that 10% should be decreased or increased? Decreased because of this gradient descent update, right? And how much? In proportion to its original probability value, right? So if that probability was like 0.4, which is relatively high, and then it will have the gradient which is proportional to the current value, right? And so it will be more suppressed, right? It's like, so do you guys remember kind of similar updating? Similar updating pattern. Okay, bonus point. So if you can answer this question, and then I give you the bonus point. So it was we discussed it very early in our lecture, maybe in the first week or so. So when do we have such amount of the gradient which is proportional to the original value? So that was like, this kind of regularization thing, right? If we do the L2 regularization, right? And then suppose we have ax plus b as our linear combination, linear regression formula. And then our L2 regularization will be some regularization parameter, maybe gamma, and alpha squared, a squared, and b squared, right? And then its gradient will be like 2a, which is proportional to the original value of an a, right? The current value of an a, so that will be our gradient. It is proportional to the original value or the current value. So if it's a larger value, and then it will be more suppressed. If it is a really small value, close to 0, and then it will be really suppressed with a small amount, right? So this kind of a gradient updating pattern is also, just to give you some So we will study in the later chapter of this CS231N, but I'm gonna just give you Oops. Go ahead. So this is a technique called the deep dream, which is imposing what the deep learning would imagine or would dream given a particular image. Okay, so this is just a grocery shop's video or a sequence of images of grocery shops, and then deep learning is actually, dreaming that there are some dogs or cats somewhere in this grocery store. Okay, so how do we achieve this kind of algorithm? So this is nothing but just creating artificially the gradient, which is proportional to our input value. Okay. Okay. So so back to this example. Okay. Back to this example. Even though we cannot directly update y's, or it doesn't make sense to even consider or think of updating y's, but that deep dream is actually making, that actually changes our kind of thoughts, and then it kind of imposes that kind of direct updates on typically those nodes that are typically impossible to update. Okay, but anyways, okay, so you guys get the idea or the intuition about this gradient caused by our softmax. Okay, and then also about this node of 0.85, and then we do not subtract 0 because that is really our ground truth node, and thus we subtract it. We subtract 1 from it, right? And thus this is our gradient, right? So this is just a side note, but so I was initially confused, or I didn't initially memorize the gradient of this softmax between like which one to subtract from the other, right? So you guys remember I was just confused, right, for a moment, right? And then when I wrote this gradient with the flipped sign, and then it didn't make sense when imagining their gradient, or which value do these values want to be updated as. Okay, but anyways, so this guy negative 0.15 is actually reflecting our intent to make this value larger. Okay, so in the case of imagining kind of gradient descent update, and then it will be like this. So it will be acting as a positive value, right? And so we want that value to be higher, close to 1. Okay, but if it is a really close, if it is a really close as maybe 0.99, and then correspondingly the gradient will become much small, right? Because the difference between these two will be really small, right? And so the gradient will be small, and thus our network will not try too much to increase that value. Any questions so far? Okay, so related to this issue or this perspective, back to this example of fully connected layer. So suppose we obtained a dy, and then why do we need to compute both of dw and dx, or maybe dx as so this is a matrix version, or small x is just a vector version of an x. But why do we need to compute both of them, right? So in the case of dw, how do we use them? So once we obtain the dw, and then how do we use them? So they will be used to directly update our current w, right? Right? Suppose our current w was maybe 1, 0, 1, 2, 3, negative 1. Suppose this one is our current W, and then suppose we obtained dW as some matrix. And then we just multiply the step size and then subtract it from this the current matrix. So that's how we update our W, because W is our parameter that we directly update, right? But what about dx? Should we, do we need to compute dx at all? So if it was our initial input node, and then we wouldn't need to compute the gradient with respect to x, but in general, this fully connected layer can be placed in the middle of our entire network, right? And then what is our x? So x will be the output of the previous layer, right? And so we need to provide dy to that previous layer, or the gradient of the output of the previous layer, right? So dx computed in this step is used as the gradient of the output to the previous layer. So we need to compute both of them in general in almost all cases. Any questions so far? Okay, so probably that's it for the backpropagation. Okay, so now this is probably the hardest part, or most difficult part when studying the deep learning. So once you mastered how this backpropagation works, and then the rest of the stories are in deep learning, yeah, it's relatively easy, I think. So okay, so let's move on to the next chapter of the convolutional neural nets. Okay, so let me address this question about the inner product computation, mainly used in the CNN operation. So convolution is basically an inner product computation, right? And the inner product computation, intuitive understanding of this inner product computation is to compute the similarity between the two vectors by using the inner product, okay? So I'm not sure if I explained it or not, but so you guys know the cosine similarity, right? To measure or evaluate the differences or similarities between the two vectors, and this cosine similarity is defined as this guy, the inner product between the two vectors, and right. And so if our vector was maybe 2, 1, and maybe 1, 3, and then the inner product is what? 1 times 2 and 3 times 1, right? So that's the inner product, right? And then in the case of a cosine similarity, we normalize them based on their lengths, right? Okay, so Okay, so this is our cosine similarity, and thus we can even obtain the angle over here, which is what? 45 degree, right? Okay, so the main idea of the cosine similarity is that if the the angle between the two vectors are small, and then we treat those two vectors being similar to each other, right? So that's the main idea of this cosine similarity. So that's a very basic thing, right? And here, in many cases in deep learning or many other applications of machine learning, so we sometimes just omit this length normalization when computing the similarity between the two vectors. Okay, so in many cases, just computing the inner product can work as the similarity measure. Okay, so what's the difference when using the inner product as a similarity when compared to cosine similarity measure? So yeah, if we have really long vector, and then even if that vector has a large angle with the other vector, and then if that vector length is really large, and then it will mostly have large inner product similarity with the other vectors, right? So it's like making this a similarity game unfair, because we are giving, like, regardless of whatever the other vector is, if one particular vector has a really large length, long length, and then it will mostly have a large similarity with the whatever the other vector is, right? But that is okay, right? So that is okay, because our neural net will handle this issue through our backpropagation. So if we use this imperfect inner product measure as our imperfect similarity measure, okay? If we just use an inner product, and then that should be okay. Through our backpropagation, those imperfect similarity measure will be kind of considered and adjusted through like optimizing other parameters, okay? And also, there are some cases where this inner product similarity makes sense as well. So suppose a particular vector is really having a large similarity with most of the other vectors. Okay, so if you remember the role of the bias in our softmax layer, or maybe softmax classifier, right? So if we add or if we assign more bias or larger bias value, and then it's like we are giving more probability even before looking at the input image. So we are giving larger probability to that class, right? So that way we may want to give some bias or some more probability or similarity to a particular vectors, right? So that way this inner product will work as a similarity measure just okay. So, and also this cosine similarity, the main kind of issue of this cosine similarity is that this length computation is sometimes quite burdensome, okay? So this inner product is really, really simple, and that can be highly optimized or highly parallelized through our GPU, okay? Like NVIDIA's 1080 Ti or 2080 Ti, which is recently available. And all these GPU computations are nothing but just making inner product parallel, okay? Or this inner product in general can be represented as a matrix multiplication. For example, if you saw this matrix W and maybe X, maybe we have more number of an X, okay? So this is our X, which is our batch, which is in 3-dimensional, and our batch size is 5, okay? So in this case, it's all about the inner product, because so we have an inner product over here, and also inner product over here, and over here, and so on. So how many inner product do we have here? 10 inner product between two three-dimensional vectors, right? And so it's all about the inner product. And GPU is nothing but the device that does this inner product computation highly parallel. Okay. So that's the introductory kind of justification of the use of the inner product in the case of a convolutional neural nets. Convolutional neural net is also the inner product. Let's see. Okay, so you guys know how this inner product works in the case of convolutional neural net, right? So suppose we have maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, and our filter is maybe 1, 1, 1, and 0, 0, 0, 0, 0, 0. Okay, and then if we just compute the activation on that particular position, and then the inner product, I mean the output, activation output will be 15, right? Because we are doing 9-dimensional inner product, right? And 9-dimensional inner product is repetitively done by just moving one by one our filters, right? Horizontally and vertically, right? And then, the reason why I mentioned or I discussed about the inner product as a similarity measure is because this convolution can be viewed as just computing this similarity, okay? Similarity with this fixed filter, okay? By just moving it around in our image horizontally or vertically, right? So we just compute the similarity at each different position and evaluate where is the position that has the highest similarity kind of thing, okay? So that way it is also when computing this output of this convolution, and we sometimes call it as activation map, right? So this activation map is typically referring to like the input or the output matrix between the convolutional neural net or convolution layers, right? But what is the meaning of this activation? So activation is really like how similar the particular position is with the given filter, okay? So it's like detecting our patterns that we look at, okay? And also, back to this inner product work, inner product similarity. We usually treat, in the context of a convolutional neural nets, we usually treat the, given our filter as like this, and then you can just, you can consider this as the pattern kind of extractor that has this kind of shape, right? So this is the most basic part of this convolutional neural net, but at the same time it's a little, kind of difficult to explain, or a little bit tricky. Most basic things are the most tricky thing to explain, but so suppose your filter has like this, and then in some high dimensional space, or maybe 9-dimensional space, right? And then this filter will have the fixed direction and maybe length, right? Okay. And then suppose we have a really big image, okay? And then we move or we match this filter at this position or at this position and so on. And then you can imagine each different places we will obtain different 9-dimensional vector, right? And that 9-dimensional vector will be placed over here or over here or over here, over here, and so on, right? And then if we just compute the inner product with this guy and this guy, and then we consider the length of these two, and then also the angle, right? And then now let's imagine, I mean, this is just a one kind of a simple approximation that we impose, but yeah, stochastically or on average, at each different positions, the 9-dimensional vector length coming from our image has the same length. Okay. Again, our assumption is at each different position that we match our filters with in our image, suppose each of the different image regions has approximately the same vector length. Okay, and in that case, all these red vectors will be treated as having the same length. Okay, and then suppose that length has maybe radius of 5, and then those vectors will be on this circumference of our circle, right? I mean, this is just one kind of assumption, but yeah, let's just make that assumption, and then now inner product similarity is ending up with like really similar to cosine similarity. That, I mean, in order to have a maximum possible similarity value, and then the angle should be minimized, right? And so, given this filter vector, I mean, given this vector represented as our filter, and then when do we have a maximum inner product similarity? It will have the same direction, okay? Same direction. And then that same direction can also be further simplified, that suppose we have the same length as the filter, okay? The same length as the filter vector, and then our maximum possible similarity is obtained from the same vector as our filters, right? So my point is that if our filter, if we are given this particular filter, and then we are looking for, or the maximum possible similarity is obtained when we have the patch as this exact shape among our big image. Okay, so I mean, this is a kind of so as we imposed, there are several unjustified assumptions involved here, but you can just have this kind of intuitive idea that given this particular filter coefficient, we are looking for that exact same pattern to maximize the similarity. Okay, and if the similarity is not maximal, and then maybe that filter, I mean, that region may have like this kind of pattern, which is not exactly the same, but almost the same. So in this case, the similarity will be non-maximal value, but it is relatively high, right? Any questions so far? So let me give some example. Okay, so suppose these are, I should have started with this simple example, but suppose we prepared for these 3 different filter patterns, right? And then suppose this is our original image, where this black ones representing -1, and white ones is representing 1. Okay, and then if we just move this filter around, let's see. Okay, so at this particular position, we will have a perfect match, right? So in this case, if this region, this region has exact same values as that filter pattern that we are looking for, and then in that case, the inner product between this filter and that region will have really the maximum similarity value, right? Even though we we computed the inner product and then we just simply divided it with the number of dimensions, but that's just some additional kind of things. Okay, so if we just apply it into different region that doesn't exactly have the same pattern, and then the activation will be smaller than the maximal activation of 1. Okay, so this is our final activation map. Okay, so that means when using this filter at this position where this part is centered at this position, and then we have over here we have a maximum pattern matching or maximum similarity that we can get, right? And so we obtain the maximum similarity over here and over here, which is corresponding to those two positions, right? And then over here and over here. So in that case, we apply this part, and that will also have the exact match, right? And all the other parts, they will not have the maximum kind of similarity value, right? Because the patterns are not exactly matching, right? So this guy is called the activation map, which means how much activated a particular region in our image by matching it with our given filter. Okay. So I hope it gave some intuitive understanding or explanation about the inner product, the notion of the inner product used for the convolution. And then, is there any other methods or other ways to compute the activation output? I have no idea. Yeah. Is there any other ways that you guys seen?
I just had a question about the previous part.
Okay.
You said that you can learn the normalization part by backpropagation. But how then do you account for different brightness areas in a picture where you put the same convolution over every pixel?
You mean in the case of a bright region, and then we will get mostly high activation? Is it?
It seems like this.
Yeah, right.
Or the reverse would be the same.
What's that?
Or the reverse. Like
Yeah. In the opposite case, you mean? Dark regions will have mostly low activation, right? Okay, so in this case, so that is related to this assumption, or here we assume that each different locations will have the same vector length, right? So in mostly like bright regions, and then it will have a relatively large length than the other regions, right? So in that case, regardless of whatever particular filter shape that we match or compare, it will mostly have the high activation value, because from the inner product, I mean, that region itself has really large lengths of the vector, right? Yep, so that is the limitation in general of the inner product, which is used as a similarity measure, right? But that is also considered, like in this particular case. So for those regions that we impose our patterns, if we can freely, we can set their values as positive values, but at the same time, for those regions that we shouldn't we should not match, we can assign the negative coefficient, right? So if the regions are all bright, and then we can approximately have all the ones in all these 9 different locations, right? So in that case, the activation value will be negative values, right? So we can kind of manipulate our filter coefficients so that we can kind of penalize all the bright regions or the dark regions and so on. Okay. Any other questions? Okay, so other than the inner product, to my knowledge, I don't have any idea. So typically, I mean, inner product is a really simple operation, right? And so we usually define our convolution as really this simple operation. And then if we want to make our model more complicated or more capable, and then we typically we combine them in many different ways, like stacking them into multiple layers, and also in the case of within a single convolutional layers, we usually have the same number of, same filter size, right? So in the case of let's see. Okay. So this is representing one single convolution layer. How many convolution filters do we have here? So this was one of our quiz problem, right? So if we have output activation channel that has the depth of 6, and then it means our filters, the number of filters is 6, right? And then also, let me also check the other problem in our quiz. So given this input activation map, what's the depth of our convolution filter? 3, right? So somewhere in the other slides, so there was a kind of a note or mentioning that we always fix the full the depth of our convolution filter with the full depth of the input activation map, right? And so if we are given input channel S3, and then each of our filter in our convolution layer will have the depth of 3, right? But anyways, if we have 6 different convolution filters within a single convolution layer, and then we obtain 6 different activation map, thus resulting in like 28 by 28 by 6 as our final activation map, right? And then here, you guys understand this stride, right? and also padding size, and also convolution filter size, right? And then within a single convolution layer, you can just manipulate them, or these are the hyperparameters that you have to choose, right? And then can we, is it possible to make this convolution layer more interesting so that we have a different size of filters within a single layer, or different stride size or padding size as well? So you can certainly define such more interesting convolution layers as well, right? So in that case, suppose among the 6 convolution filters, 2 of them are 3 by 3, okay, 3 by 3, and maybe 2 of the other filters will have 5 by 5 convolutions or filter size, and of course the depth should be 3, right? So in that case, what is the problem in this case? What is the issue?
Output sizing.
Output sizing. Okay, yeah. So if we don't allow any paddings over here, and then you guys know that activation map in terms of a width and height will be decreased when using a larger filter size, right? Larger filter size. Okay, so that is the issue, right? And so each activation map over here, which is one thin matrix, will have a different horizontal or vertical size, right? And then how can we match them? Can we match them? I mean, how can we match them? We can simply change the padding size for each different filter size, right? So usually in the case of, so that was another quiz problem, but in the case of 3 by 3 convolution filters, and then how many paddings do we have in order to have the same width and height between input and output activation map? How many? 1? Or what about 3 by 3? It's 2, right? So for different filter size, we can definitely use different padding size, right? And also, this is about the basics of the convolution, but you can think of when thinking of the output activation map, and then suppose we apply the 3 by 3 filters, and then for one activation map, you can always think of it. You can always think of matching it with the center position in the matching regions. So if we just apply our filter at that position, and then we will obtain some activation map as a scalar value at that particular position, and this value, you can think of this value belonging to this guy, okay, this single pixel, okay. So this activation value is belonging to this single pixel in our input, okay. So if we just align this the center pixel in this manner, and then this should be one of our input pixel in our image, and thus it can be over here and over here and over here, right? So if this guy was a center pixel, and then we need still one more pixels on the right, and so we need one more kind of line on the right vertically, right? So back to this guy. So we have this filter to match among different locations, and then I mentioned that the center pixel will have the activation as 0.77, and this center pixel will have the activation as 0.1, right? So that way, even though the convolution, one convolution operation will involve multiple pixels within that filter size, but you can always map this kind of one-to-one mapping between these pixels between input and output images. So you can think of it that way to help you understand this better in terms of the padding size needed and things like that. Okay. Any questions so far? Okay, so so we now understand that we have no problem of using different filter sizes within a single layer, and then in order to make the same width and height in terms of an activation map size, we can adjust the padding size accordingly. Yeah. But sometimes so I need to explain the application of this convolutional neural nets in the case of a text data. Let's see. Let me see if I can explain it quite quickly. So this is one really famous example where you can where the convolutional neural net was applied to the text classification. Okay, so image data is not the only application that CNN is applied. It's actually applied to many other data, such as time series data or this text data. Yeah, so this is one example of the text data, and then this is the so in this case, the text data is what is width or height? So in the case of text data, it is just a one-dimensional data. Okay, unlike the images that has the two dimensions of width and height. But in the case of text, we have this one dimensions, right? Which is the order of words that appears in our sentence. And then here, let's suppose the task is to classify the given sentence as being positive or negative sentence. Sentiment. Okay. So like, this movie is really awesome, and then it should be classified as positive sentiment, or this movie is awful, and then it should be classified as negative one. And then, so this one is actually our each pixel. Okay, so these are each pixel, just like our 2D images, and each pixel is originally represented as how many dimensional vectors? Each pixel is usually represented as 3-dimensional vectors in terms of RGB values, right? So already one particular position, that position is represented as a vector, right? In the case of an image. And also in the case of text, we have a way to represent each word, which is corresponding to our pixel, as a vector, right? As a fixed dimensional vector. And that fixed dimension is 5, okay? And then now this is a one-dimensional data, and thus if we imagine the convolution layer over here, and then this is our depth. This is our depth or channel, and thus our convolution is filling out the entire depth. But what about our filter size? So this is a one-dimensional data, and thus our filter size is just one-dimensional. So like if our filter size is 3, not like 3 by 3, and then our filter is like this, okay? And then if our filter size is 4 or 5, and then our filter size is defined as maybe like this, right? And then we can define our filters having this variable lengths, and 2 and 3 and 4 and so on. And then without using any paddings, we can obtain different activation maps. Different lengths of an activation maps. So So if our filter size is just 2, and then 1, 2, 3, 4, 5, 6, 7. So it has the length of 7, and then the activation map is having the length of 6, right? I mean, without allowing any paddings. If we use the filter size as 3, and then, yeah, we will have the size of 5, okay? Okay, and then we have all the different lengths of an activation map coming from each one-dimensional convolution filter, and then how we merge them is through like pooling over time. So pooling over time again. So in the case of pooling, we have a fixed size of a pooling window, right? But in this case, we actually have the variable size of a pooling window, and that pooling window size is actually the same as the activation map. So if our sequence length is 4, and then we just do the max pooling over all the 4 values. Like if it was 1, -3, and 3, and 5, and then if we do the pooling, and then we will obtain a scalar value of 5, and then maybe this 5-dimensional vector was -3, 2, 1, -1, and 0, and then if we do the pooling and 2, right? And then we can just concatenate them into one single vector, and that vector is given to the next layer's output. Okay. So this is one example that kind of diversified our convolutional layer setting by having different size of different size of filter size, and even we use a different stride size within a single layer. Yeah. But anyways, so the time's up, and also yeah, the homework is due this Wednesday. And also, since we have the Wednesday as a holiday, and then I will post some online lecture videos that I will record and upload, and then you should watch them and study them. Okay, thanks.